Okay, so we'll start. So I'll start from where we left in the last class. Okay, so we're discussing the non-relativistic limit of a Dirac equation in the presence of electromagnetic field. Okay? And this is what we obtained. Okay, so these are the two equations in. So this is not this one. This one. Okay, so these are the two equations, one in phi and chi. Okay, and now we are concentrating on the non-relativistic limit, and in particular, we are doing the zeroth order calculation. Okay, so so this is the expansion of this factor. Okay, and we are looking at what happens at zeroth order. Okay, and we obtained this relation at zeroth order. Okay, and now we want to simplify it. Okay, and let us see what we get. Okay, so and we have also shown that this zeroth order Dirac equation, okay, gives me the Pauli-Schrodinger equation. Okay. So now we are simplifying, try to simplify this term. Okay, sigma dot p minus e by c a. Okay, so let me redo this calculation a bit. So there are some mistakes. Okay. So let me redo this calculation. Okay. So we're looking at the term which is sigma dot p minus e by c a square, and which should act on phi. Okay, so this I can write as sigma I, sigma j, and pi minus e by c ai, and pj minus e by c aj, and this will act on phi. Okay, and note that these p's are operators. These are basically operators. Okay, at this stage. So sigma and sigma j. Now I will use the property of sigma matrices. Sigma and sigma j is identity times delta ij plus I times epsilon I j k sigma j. Okay. So if I use this here, what I'm going to get? I will get delta ij, okay, plus this term. Okay. So if I consider the term involving delta ij, I will get this term square. Okay. So the first term will be p minus e by c a square acting on phi. Is this clear? Delta ij, when attached to this term, these two terms, I will get p minus e by c a whole square acting on phi. Okay, plus I epsilon I j k sigma k. Okay, and then pi minus e by c ai pj minus e by c aj acting on phi. Okay. Yes. Now this term, if I expand this term, what I am going to get? Okay, so I am concentrating on this term now. Okay, so the second term, okay, if I consider the multiplication, what is going to happen? Pi pj. So this term containing epsilon ij will first multiply to pi, then pj, and they will act on phi. But pi pj is symmetric in ij and this is antisymmetric in ij. So that term will go away. Similarly, epsilon ijk sigma k ai aj phi will go away because ai aj is symmetric in ij. So that term will go away. So what remains is I times epsilon ijk sigma k, okay, minus, so E by C, so minus E by C, okay, pi aj, okay, plus ai pj. This will act on phi. Okay, pi aj, okay, with minus E by C factor and ai pj acting on phi. Ai pj acting on phi. Okay, is this clear? So what is this term? Okay, so this is equal to I times, so there's a minus sign, so minus I times E by C epsilon ijk sigma k, okay, pi aj acting on phi. So here you have to know that pi will act on aj and phi. Okay, so this will be sigma k pi aj okay, this will act on phi. Okay. So this means that pi have already acted on aj, okay, and they will act on phi, minus I E by C epsilon ijk sigma k, okay, aj and pi will act on phi. Okay, so this is the first term, and the second term, this term is will remain as it is, epsilon E by C epsilon ijk sigma k. Okay, this term will remain as it is, ai pj. Okay, so this term here only this pj will act on phi. So this term is basically same as this term, although there is the index structure is different, but it is similar to this term. So pi here will act on phi, and here also pj will act on phi. But now in this term, one can write this term as plus I E by C epsilon. What I will do, since this ij is summed over, okay, I will write this first as epsilon j I k ai pj, okay, and then I will use the antisymmetry property of epsilon. So epsilon jik is minus of epsilon ijk, so that will become plus epsilon ijk sigma k ai pj acting on phi, and this term will remain as it is. Okay, now you see this term cancels with this term. Okay, and what remains is only this. Okay, clear? So here in this term, this pi will act on basically on this aj. Okay, clear? Okay. So this second term is basically this term only. Okay. But we can still simplify this, minus I E by C epsilon ijk, okay, sigma k, and instead of pi I will substitute minus I h cross del I, okay, aj, okay, and this will act on phi. Okay, and so this will be minus plus I square minus, so minus E by C epsilon ijk del I aj, okay, then sigma k and phi. Sigma k, I can write it here or here, it doesn't matter. Okay, but what is this? This term is nothing but bk. Epsilon I jk del I aj, this is a vector potential. Epsilon I jk del I aj is basically bk. Okay, so epsilon I jk del I aj is equal to bk. Therefore, the second term is actually equal to, with this factor, minus E by C, okay, minus E by C, bk sigma k phi. So bk sigma k sum over k is b dot sigma. Okay, so this is minus E by C minus E by C, and there is a h cross here. Okay, there is a h cross here, so I should put h cross here. Okay, so minus E by C h cross b dot sigma, minus E by C h cross b dot sigma. Okay, clear? So at the end, I have sigma dot p minus E by C a, its square is basically equal to p minus E by C a square, okay, minus E h cross divided by C b dot sigma and phi. Okay, there is a phi. Okay, so therefore this equation, this is like your Hamiltonian H, okay, non-relativistic Hamiltonian H acting on phi equal to ENR of phi. Okay, so let us see what is now that non-relativistic Hamiltonian. Okay. So your non-relativistic Hamiltonian is 1 over 2m, this term, p minus E by C a, okay, its square, okay, minus E h cross divided by 2mc b dot sigma, okay, and there was this phi term, okay, plus E phi, plus E phi. Phi is a scalar potential. So this is my non-relativistic Hamiltonian, and I have non-relativistic Hamiltonian acting on phi equal to ENR times phi. At this stage, we can see that the magnetic moment of electron is coming. You see, the magnetic moment of electron is directly coming from the Dirac equation as a non-relativistic limit of Dirac equation. Zeroth order, at the zeroth order. Okay. But I can further reduce, okay, further simplify this. Okay. Suppose, okay, assume for a moment, for simplicity, okay, assume that yes. So assume that we are working in Coulomb gauge. wherein divergence of A is set to 0. We know that there is a freedom in choosing the vector potential. Okay, so if I set divergence of A to 0, that is called Coulomb gauge. Okay, and further I will assume. Okay, further I will assume that this it's not necessary, but let me consider weak field limit. Weak field. So I can neglect, if I want, I can neglect A square term, but I will see whether to keep it or not. Okay. So now I want to simplify this relation. Okay. Let us assume the form of B, okay, which satisfy this Coulomb gauge. Suppose if I consider B to be half, okay, B to be, sorry, A to be, not B, A, my vector potential, A, to be of this form, minus half B cross R, where B is uniform magnetic field. B is now uniform. Okay. And I can also set phi equal to 0, but let us keep it. Okay. So you can see that this relation, okay, satisfies del dot A equal to 0. This relation basically satisfies, so divergence of B cross A when B is uniform is 0. So I am choosing Coulomb gauge, and furthermore I am choosing a particular simplified field, okay, uniform magnetic field. Okay, in that case, okay, what is, so let us concentrate now on this piece. Okay, P minus E by C A. Okay, P minus E by C A, its square is what? Okay, P minus E by C A, its square will be equal to P square. So 1 over 2m is there. So first term will be P square divided by 2m. Okay, so last term will be E square divided by 2m C square A square. Okay, minus E by 2mc. Okay, P dot A. P dot A. You remember these are operators. Okay, this is operator. So it will P dot A. Okay, that will act on phi, and then there will be A dot P term. So P dot A minus E by C, E by 2mc, A dot P. Okay, so P dot A term is nothing but minus IH cross del dot A. Okay, so in the Coulomb gauge is equal to 0. And what is A dot P? A dot P is basically, we have the form for A. This is A. Okay, so A dot P, yeah, so there is a factor 2 which will come here. Okay, P dot A, just a minute. Okay, so this is P dot A dot P, yeah, correct. So here, when I consider this term, okay, so let us, there is another term which will be there. So let us consider P minus E by C A, okay, P minus E by C A, okay, acting on phi. So this is P square by P square, okay, then there will be A square term, okay, these are there, okay. Now P acting on A phi, okay, P acting on A phi, this will come with a minus sign, okay, minus A acting on P phi, okay, so that is A dot P acting on phi, okay, and this term is there, okay. So this term basically, okay, is minus of P acting on A, okay, and then they will act on phi, minus A acting on A dot P acting on phi, okay, and then there is a A dot P acting on phi, okay. So there will be twice here. Okay, so one term was missing, there will be a twice, so this will add with this. So you have to be careful when you deal with this kind of expression. Eventually they are going to act on phi, okay. So you have to be careful in cross terms. So in the first, P will act on A phi. So this term gives me these two terms. And the second, A will act on A dot P act on phi. That remain as it is. Okay. So I have two factors here. Okay. Twice A dot P. Okay. But what is A dot P? A dot P is half B cross R dotted with P. Okay. But this is nothing but B cross R is nothing but half B dot R cross P. Okay. And R cross P is nothing but your L. Okay. So half B dot L, your angular momentum. So A dot P is nothing but half B dot L. So 1 over 2m P minus E by C A whole square is equal to P square divided by 2m, okay, plus E square divided by 2mc square. If you want, you can neglect this term under the assumption that the fields are weak. Okay, so A square will be small. Okay, but let us keep as it is. Okay, this term will go away because of Coulomb gauge, and minus 2 will go, and so I will get minus E divided by 2mc A dot P. A dot P, so that is B dot L. Okay, so this is the simplification in the first term. Okay, now we will attach this term. Okay, so H non-relativistic will be P square divided by 2m, okay, plus E square divided by 2mc square A square, okay, then E phi plus E phi, okay, and then I will write this term, okay, so it will be minus E divided by 2mc, okay, B dot L, okay, and then there is H cross, so B dot sigma. Okay, so this somewhere I missed H cross here somewhere. Okay, so when I put P, so it is R cross I H cross gradient, so it will be H cross here. Okay, so it will be H cross. So this will be plus sigma dot B. Correct? Okay. Now you see this I can write in a simple way. Okay. So this I can remove this B here, remove this B here, and I will simply consider B. Okay. But what is sigma? Sigma H cross by 2 sigma is your spin operator in non-relativistic quantum mechanics. H cross by 2 sigma. So this sigma is twice S divided by H cross. Okay. So I think I'm correct. So yeah, there should not be an H cross. So actually there is no, because H cross is there already. So There is no need of writing H cross here. Okay, so there is no H cross here. And there is H cross here. Okay, so this entire this term, okay, so the entire non-reductive Hamiltonian will be P square divided by 2m, okay, plus E square divided by 2mc square, 2mc square, okay, a square, plus E phi, okay, minus E divided by 2mc, okay, L plus 2m. Okay. Now, can you tell me what is this term? Dot P. Can you tell me what is this term?
Total angular momentum.
No. There is a factor 2, right? Here. Total angular momentum is L plus S. Now, what is this interaction term tells you? See, suppose if I have a current loop in magnetic field, okay, then this current loop in the placed in magnetic field will possess, this current loop will have some magnetic moment, okay, and the value of that magnetic moment will be E divided by mc, okay, E divided by 2mc times L. Okay, so it's considered, instead of current, let us consider a charge which is revolving in the circular orbit, okay, classical charge. Then there will be angular momentum for that charge particle. And then when it placed in magnetic field, okay, you have the energy, okay, experienced by this loop will be minus mu dot B. Okay, clear? So in that sense, this is the interaction energy between magnetic field and the angular momentum. Okay. This magnetic moment is orbital angular momentum. It is because of orbital angular momentum. Apart from that, we have this spin angular momentum. Okay, but there is this crucial two factor. Okay, so if I want to write this in the following notation, so H interaction will be minus mu dot B, where mu, okay, is, so H interaction basically mu dot B, and there is these terms also, but these are not important right now. Let us concentrate on this piece only. Okay, here the mu is basically mu orbital plus mu p. Okay, mu orbital will be given by E divided by 2mc L. Okay, this I can write as G times E divided by 2mc L. Okay, in that case G will be 1. But mu spin is twice, okay, this is two factor, twice E divided by 2mc S. Okay, so in this case your G is 2, and this is what is known as Landage effect. So for spin angular momentum, the Landage factor is 2. Okay, that is, what is important is that this Landage factor is coming as a non-relativistic limit, zeroth order non-relativistic limit of Dirac equation. So Dirac equation, okay, gives you the correct magnetic dipole moment. the Landry factor for magnetic dipole moment. This is what is observed. Okay. So this is inbuilt into the direct equation. You don't have to take any external. You don't have to add spin externally. Okay. Fine. But we'll see. Okay. Maybe if we are lucky, then we'll see in the next semester when you apply quantum field theory. Okay. There will be certain corrections to this. Okay. There will be certain correction to these two. Okay. And that correction, if I remember correctly, so there will be 2 plus or minus 2, okay, so 2 plus 0 point, okay, some factors are there, okay, and there will be some 8, 4 something, okay. So there are up to, this is 11 decimal places. Okay. Up to 11 decimal places, okay, the answer given by quantum field theory matches with known experiments. And that is the biggest triumph of quantum field theory. Up to 11 decimal places, okay, these numbers are same, whether you can, as predicted from quantum field theory. Okay. If you calculate it by experiment, by doing experiments, okay, you get some number. That number matches up to 11 decimal places with the answer predicted from quantum field theory. So in this sense, it is the unique theory which has such a precise matching with the experiment till date. Okay. There is no known theory which has such a unique matching with the experiment. Till the 11 decimal places, whatever these numbers are, they match with the corresponding results in quantum field theory. So the quantum field theory basically gives you the corrections, but the reason for those correction is very is drastically different. This correct reason for this correction is quite different. It basically has to do with the fact that electron and your proton, okay, or whatever the charged particle, when it interacts with electromagnetic field, okay, it emits and absorbs. So basically, your electron here, okay, and suppose there is another charged particle. Okay, let us assume there is a proton, okay, and this is the electron. Okay, so the interaction between them is via the exchange of what is known as photon. Okay, so this electron emits and absorbs photon. Okay, and that gives you the correction, further correction to this. In this picture, we cannot accommodate this because when you say emission and absorption, the particle number is not conserved. So basically, the quantum field theory gives you the correction to this result, which is obtained by Dirac theory. Okay, but there is more to. So forget about the quantum field theory right now. Okay, there is more that Dirac equation tells us. Okay, see, we are looking at only the 0th order piece. Okay, we are looking at basically the 0th order piece. Now you might be wondering what this next first order, second order, what they will do. Okay, so what they will do is the following. Okay? Suppose now you consider, so this is what we get. Okay, this is what we get when we set up the magnetic field in this way. When we set up the magnetic field in this way. Now let us switch off the vector potential. Okay, and let us keep only the scalar potential. Okay, this phi. And let us for the moment you assume that this is inverse square potential 1 over r. Okay. In that case, okay, these second order terms, okay, first order, second order, third order terms will give us different terms. Okay. At the first order, you will have relativistic correction, which is, okay, so if phi equal to say 1 over r, then you will get 2 this p square by 2m, okay, minus v of phi, that is so v of r, that is just this, it is just this phi. Okay, you get some corrections here. Okay, so this is your zeroth order Hamiltonian. In this case, when I set vector potential to 0 and scalar potential to 1 over r, then this is my zeroth order Hamiltonian. In our case, whatever we discussed, this is my zeroth order Hamiltonian, this one. Okay, H non-relativistic is actually zeroth order Hamiltonian. Okay, now I am changing the problem. I am setting the vector potential to 0 and phi to be 1 over r. So I will not get this kind of thing. So what I will get here is correction t to the power 4 divided by 2mc square. Okay, then there will be some other term which depends on the gradient of, so I'm not precise here, there are some numbers and etc. Okay, which is gradient of phi, okay, times there will be certain correction. So this is basic. So let me write it in a precise way. Okay. So this is zeroth order Hamiltonian, and then I will get minus t to the power 4 divided by 8m cube c square. Okay, that is one term. Then I will get some constant, that is 1 over 2 m square c square, okay, into 1 over r dv by dr. Okay, dv by dr, it is d phi by dr. Okay, and s dot l term. Okay, then I will get plus, I will get h cross divided by 8 m square c square. Okay, gradient of Laplacian square of phi. These are the corrections which are going to get. Okay, but what is this potential? This is basically hydrogen atom. So we are basically discussing an electron, okay, in the hydrogen atom. So you get all these corrections to your usual hydrogen atom spectrum, and this is observed. Okay, so this is called relativistic correction. Okay, this is spin orbit interaction. And this new term is called Darwin term. Okay. We are not going to derive this, but in the next class, what I will do, I will give the physical meaning to this, all these terms. These terms we already expect. Okay, these kind of terms we expect. Why we expect this kind of terms? So suppose if I consider energy momentum relation, E is equal to P square C square plus M square C to the power 4. Okay. So the first term in this is MC square. Okay. Plus then I have P square by 2M. Okay. Then I have P to the, if I expand this, then I will have P to the power 4 divided by 8 M cube something. This term will be there. Okay. So this is the next relativistic correction to H0. So this rest energy we always neglect. Okay. We don't take into account into H0. It is there still. Okay. So rest energy together with this term is H0 basically, but normally we don't take into account rest energy. Okay, because I can set, because I can always choose my relative energy scale where this is set to 0. I can change my energy scale. So this H0 will contain this term together with this 1 over R. The next term, this term is basically coming from the expansion of the square root, roughly. Okay, these are due to the presence of spin in the Dirac equation. Okay, these two. Okay, so in the next class, I will speak more about these two terms. Okay, what is the meaning of this term and this term? Okay. There is a systematic way to get the non-relativistic limit order by order, okay, from the Dirac equation. Okay, non-relativistic corrections order by order, okay, to Dirac equation. Okay, but that we are not going to do. It is called Foldy-Watusian transformation, what is known as transformation. Okay, so with using this technique, one can get one can have a systematic way to discuss the non-relativistic correction to non-relativistic Hamiltonian. Okay. There will be other terms, higher order terms. Okay. But the first order term is this. These terms are basically responsible for give you this energy splitting, the splitting in energy levels of hydrogen atom. Okay, and those splittings is actually observed, the splitting of this energy levels, and the extent of splitting, okay, is precisely in agreement with the expected results from this correction. So if you apply your perturbation theory, okay, with this as perturbed Hamiltonian, okay, then the splitting which you get in the ground state, in given energy state, okay, matches with the experiment. Not with this degree of accuracy, but this is a unique feature. Okay. Fine. So you see the Dirac equation encodes the information about the spin. It is there. You don't have to substitute by, and that is the important lesson. Okay. So if you have any question, you can ask. Maybe
Sir, in this equation, phi is still a two-component vector, right?
Where this phi is a scalar potential.
No, I mean the wave function that we chose, the
Yeah, yeah,
equation.
yeah, yeah, yeah. Yeah, yeah,
That is,
correct. So this phi, yeah, this phi is the two component spinner. Okay.
so
But
what
you see,
what is the interpretation of that?
so this is, so yeah, that I actually forgot. So it's good that you asked me this question. Okay. So you come back to this expression. Okay. This one. This one. Okay. So what we did, we evaluated chi from this and substitute here, and we got the equation in phi. Now, when we solve this, we will get phi. Once we know phi, we will get chi. Okay, but you see, there is a difference between phi and chi. Okay, in the non-relativistic limit, okay, in the non-relativistic limit, okay, this chi will be relative. Chi will have a relative separation factor compared to phi, and that separation factor is basically of the order of v square by c square. Because of this plus sign and there is a minus sign here, you see how this e minus, what is the sign of this term? It is a minus mc square. Okay, and there is a plus mc square. Okay, so in the non-relativistic limit, this phi, okay, is called large component, and this chi is called small component. Why this large and small? Okay, because this factor, okay, if you take non-relativistic limit, one can see that phi is this chi is smaller than phi, okay, by factor v square by c square, or this your that e minus e phi enr minus e phi divided by 2 mc square, this factor. So this component is the smaller component than this. So in the non-relativistic limit, this will exceed over this. Okay? So there is an asymmetry between this phi and chi. Okay? They are not at the same order in the non-relativistic limit. Okay? These contribute more to your total wave function, to your psi, than this. Okay? Yes. So we have not yet. Please don't be under the assumption that we have solved the problem. We have not yet solved. Okay? We just took the non-relativistic limit and just verified that we are on the right track, in the sense that we are getting the known theory. That is the first requirement of any physics, any physical theory. Whatever you are proposing, okay, in certain limit it should match with previously existing results. That is the first requirement. If it's not matching, and if you are proposing something new which is not matching with the already established result which are valid in certain regime, then your theory is incorrect. In certain, your Einstein theory in non-relativistic limit matches with your Newton's laws of motion. That's why people take it serious. On top of that, it gives you certain extra features. But the first requirement is that in certain limit, it should match with existing results. That is what we checked. That is what we verified here. Okay. In the non-relativistic limit, we expect Pauli-Schrodinger equation, and that is what we got. In the non-relativistic limit, we expect if we choose a magnetic field in particular way, then we expect the S dot B interaction with correct Lagrange factor. That is what we got from the Dirac equation. But that does not mean that we have solved the problem. The problem is still there. We have to solve this. Okay. These are two equations, and we have to solve that. But I'm not going to do that. It will take huge time. So what one can do, one can set first A equal to 0 and take this scalar potential to be 1 over R. Okay. So that is basically saying that we are discussing the Dirac hydrogen atom. Okay. But that I will give as a big lab assignment. All these solutions of Klein-Gordon equation, Dirac equation, okay, that I will give as a lab assignment in the next semester. You have to use the series solutions and all those things. Okay, it is done already in the textbook. Fine. So the important thing is, so as far as interpretation of this phi and chi is concerned, at this moment I can say that this phi is called larger component and chi is called smaller component, in the sense that this is suppressed than this by factor v square by c square. Okay. If you solve this problem for this inverse square potential, okay, then you will get, apart from your spherical harmonics, you will get spin contribution to it. It's called spin spherical harmonics. Okay. You expect some spherical harmonics kind of structure, right, for angular part of your equation. Apart from that, you get some, there is some extra thing to your usual YLM. It's called spin spherical harmonics, or half integer spherical harmonics. That is what you are going to get. Okay. And as a non-relativistic limit, you recover your usual wave function for hydrogen atom in the as a zeroth order term. That you can easily see. But for that you have to solve this. Okay. So since your phi is 1 over r, it is spherically symmetric. So natural way to solve this is to go into spherical polar coordinates. In that coordinates you have to solve this equation. Okay. Yeah. Any other question? So we have completed the free particle solutions. Okay? The free particle solutions are complete now. Okay, and we have seen the non-relativistic limit of Dirac equation when coupled to electromagnetic field. Okay, from now onwards we will start with the more rigorous study of these spinors. Okay, for that we need we have to revisit to Lorentz transformation, and we will see what are the transformation properties of this Dirac, the four component object. It's more to it. Okay. Then we will systematically study the spin and etc. But I don't know how much time I will get. But I will, whatever it is, I will continue. Okay. When exam is declared, okay, I will set some deadline. Okay, and on that date I will stop. Okay, and after that, again, whatever remain in this course, I will put it in the next semester. Okay. So if you have any question, you can ask. Otherwise, I will end the meeting.